Hamiltonian form. Automatically closed Keller. We are in Keller situation, every holomorphic form is
on
closed.
the left side, when you say it's a non-degenerate, it's 2-0 form.
No, not automatic.
So you would have
all
to-
conditions together. It has to be Keller. Did I put it? I think complex hyperkahler Keller something. So, and in fact, the first examples of non-Keller varieties with 2-0 forms were obtained by Guan exactly by very similar construction to what we discussed about A2, about abelian varieties. It's a small variation, but then it can be done very soon. It happens that it works.
So I'm still confused. So this G hat is the symplectic form which corresponds to the metric?
Yes,
or
it's a form.
It's a form.
You have to sign, look, this is a form, so you have to sign the same object. Same object.
But then again, the one with the bar, how again I'm confused. Is it
Bar, yeah.
just the
It's
bar?
dizzy, it's a dizzy bar.
Ah,
You obtain an element, the form, so the condition is square has to be equal to 0. Square is square nth power. Okay, so nth power. I wrote square for dimension 2 n power. But here maybe I would. Okay, I want to come to the main kind of to the main sort of topological properties of this variety, and that in fact, you see, I wrote 2 here. That was a mistake. Because 2 is for gas resurface. So in general, I have to put 2 into power n. However, and that's exactly one of the properties that if you consider the classes h2 of x, and we take x to the power n, we stretch it to h2n. Now, the point is that in this case, there is a form, there is a quadratic form, Q, on H2 of x, such that x to the power 2n, I hope I'm correct, is q of x to the power n, which is quite rare. So in general, so if you look at the arbitrary variety, yes, and you consider the nth power, it's a form of degree. So if the power is 2n, form of degree 2n, 2n. However, in this particular case, we have this strange phenomenon that it's exactly a power of there is a quadratic form. And that was something which didn't allow me to believe that they exist, because what we are getting is the following. So suppose we look at Hodge kind of, okay, HPQ. Yes. And we have, here we have elements. So this is H2. H0, H02, H1. So we have a sum, these forms have a sum, dimension 2. And now, the property that the form, so in order to be, so if you have 2-0 form, yes, and the power n plus 1 is 0. Just not enough variables. We have dimension 2n, 2 by, and so for 2n we obtain volume form, holomorphic volume form, e to 0 to the power n, volume form, and then we have to have 0 here. So therefore we have plenty of, so you see the property that VT, the class. Now, suppose we have the class VT inside here. It's inside H2. And this class may appear as a holomorphic form, on some variation, only if Vt to the power n plus 1 is equal to 0. If Vt appear as a class, not a form, but just a potential class, potential solutions class on some deformation xt. Yes. So, but the idea that but then you have the number of equations is all upper there. So you have plenty of zeros. In dimension 2 it is 1, 0, and it is naturally quadratic. In high dimension, you formally speaking obtain a lot of equations. But if you consider deformation theory, and there is a special argument which I brought up, it was quite simple and then extended to arbitrary canonical class, that in fact there are no obstructions, so no obstructions to deformations. And then deformation space by Fedor, local variations are given by H1 xt, tangent bound. So it's essentially cosmology with respect to tangent bound. So you could think about it in the following way, very naive way. Just imagine that your variety is covered by balls, let's say, by simple complex ball. And there is a gluing. So now you start moving them. Their structure remains the same, but you're just moving them with one with respect to the other. Then on the intersection you need some condition compatibility, and this is H1. In general, and this really occurs in some cases, you need kind of to adjust also triples of such subsets. Yeah? And that is obstruction in H2. So you resolve obstruction in H1, but then you resolve obstruction. You have to so you can kind of create a small variation, infinitesimal variation by any element of H1. So any theta here creates an infinitesimal variation. But then you need kind of, how to say, that means you just glue the way you glue the ball. But then you have triple. And it's usually, to adjust triple, you need something in H2. And therefore there is an obstruction in H2 of xt. But in this case, in Kara case, and in fact, that's, I don't want to dive into this. It is easy to show that this H2 is actually, so what is T? T is actually omega 1, is omega n minus 1. So in this case, we have canonical class is trivial. So therefore, tangent bond is isomorphic to omega 1, and in fact, you can see it on this term, dual tangent bond is dual to omega. You see what is, after all, the form, 2-0 form provides an isomorphism between a dual to tangent bond and cotangent bond. So therefore, what is the advantage of omega n minus 1? That this cohomology already here. So it's not in general, this bond is some bond, and the interpretation of this cohomology, how to say, is maybe quite non-trivial. It's not a Hodge cohomology. It's something, two cohomology of a bundle. But in this case, we can interpret it in terms of Hodge bound, and therefore take integrals, and then it's easy to prove that there is no obstruction. But then the point is that now, if there is no obstruction, then you actually can write, put in here any theta, and then So that's how a form appears. So you actually can adjust any deformation here by some coefficients with t squared, with 2 parts.